Okay, guys, welcome. Today we're going to talk about combining probabilities. Now, what I mean by combining probabilities we'll talk about the probability of either more than one event happening or one or another event happening and things like that. Okay, so the first type of probability that we're going to discuss is when we want to look at an AND probability. So probability of A and B, right? Now, first we're going to discuss this for what are called independent events. Now, what makes an event independent? Well, we say that two events are independent if the occurrence of one event does not affect the probability of the other event, right? So as an example, you might say something like, let's see, two events here. So one event would be that, let's see, LaSalle is in Philadelphia, or it is raining, right? These would be two independent events because if it's raining, that doesn't affect whether or not LaSalle is in Philadelphia or not. And the fact that if LaSalle is in Philadelphia or not doesn't affect if it's raining, right? So it's kind of a silly example, but that's the idea. Now, if you have two independent events, A and B, with their individual probabilities, probability of A and probability of B, then if we want the probability of both of them occurring, we're just going to multiply them together, those probabilities. And of course, you could extend this to any number of independent events. If you have 4 independent events and you want to know what's the probability that they all occur together, we would multiply their probabilities together. All right. So as an example, we want to find the probability that a 100-year flood, which is a flood with a 0.01 probability of occurring in any given year, will strike a city in 2 consecutive years. And we'll assume that a flood in 1 year does not affect the likelihood of a flood in the next year. So this sentence here gives us the independence that we need. So this is independence, right? So we want the probability of a flood in year A and a flood in year A plus 1. Well, the probability of getting one of these in any given year is 0.01. And if we're told that these are independent, then we're just doing 0.01 times 0.01, which means that I'm going to have 0.0001. Right? Once I multiply them together, I'm going to get a 0.0001. All right, so that's the event of this flood occurring. Now, example 3, what is the probability of rolling 3 6s in a row with a single die? Now, again, remember that the probability of getting a 6, of course, is 1 out of 6, right? Now, we also have to ask ourselves, are die rolls independent? And of course, the answer is yes, because just because you roll a 6 on the first one doesn't make you any more less likely to get a 6 on the next one. The probability is still 1 out of 6, right? So then the probability of a 6 and then a 6 and then one more 6 would be 1 out of 6 times 1 out of 6 times 1 out of 6, which I guess would be, so I would need to do 36 times 6. So then let's see, that would give me, I think it's going to be a 216, but let me double check. Yeah, 216. So we get 1 out of 216 there. So that's our probability of rolling 3 6s in a row with a single die. Okay, so it's fairly easy for independent events. Now, if you have that 2 events are dependent, that means, of course, the opposite. That means that the outcome of one event would affect the probability of the other event, right? So for example, let's think of 2 dependent events. Right, so for example, we might say that one event is it will thunderstorm today. And we'll say that another event is I will walk outside today. Well, if it thunderstorms outside, you may not end up walking outside today, right? So the fact that if there was a thunderstorm today is going to affect that you will walk outside today makes these events dependent, right? Now notice that it doesn't necessarily work the other way, right? If you walk outside, that doesn't make it any more or less likely that it will thunderstorm, but you just need it sort of in at least one direction. Now the probability that two dependent events both occur is the probability of one event, and then we times it by the probability of the other event, given that that event has already happened, right? So again, probability of B given A means that the probability of event B, given that A has already happened. And of course, you can extend this to any number of dependent events. Okay. Now, the game of bingo involves drawing labeled buttons from a bin at random without replacement. Now, there are 75 buttons, 15 for each of the letters B, I, N, G, and O. Now, we want to know what is the probability of drawing two B buttons in the first two selections. We want probability of two B's first, right? Well, let's think about this, because the probability of the first B is going to be, well, there's 15 out of 75, right? Now, the fact that you are not replacing them means that on the second draw, you're only going to have 74 to choose from now, right? So the second draw being a B, given that the first was B, means that we have 74 to now choose from, and we also have one less B to choose from. So the probability that these first two draws are both B's would be 15 over 75 times a 14 over 74, right? So if we multiply this out, we have a 15 times a 14 in the top, which would give us a 210, and then a 75 times a 74 in the bottom, which would give us a 5,550. And if you wanted to find the percentage here, then you would get that this is roughly about a 0.03784. All right, so a little bit under 4% chance that this happens, right? But the idea is that since you're not replacing these buttons, you're going to have different probability on the second one, and that makes them dependent events. Okay, in the next example, we have that a 3-person jury must be selected at random from the pool that has 6 men and 6 women. We want to know, what is the probability of selecting an all-male jury? Okay, so we need 3 people. Now, the probability that the first is a male would just be 6 out of 12. Right? Because you have 6 men and 6 women for 12 people total. So the probability of selecting a male is 6 out of 12. Now, the probability that the second is a male, right, would depend on whether or not you chose a man or a woman on the first time. So this is the second is male, given that the first was male. Should be really saying given. Well, you now only have 11 to choose from, and you also are now down to 5 males to choose from. And then, of course, similarly for the third male, given that the first 2 were male, you're now down to 10 people to choose from, but only 4 males. So now the probability that we have all males in this case will be 6 out of 12 times 5 out of 11 times 4 out of 10. So if we do this in the bottom, we're going to get, let's see, that would be a 1 1210, I think. And then in the top, we're going to get a, let's see, a 30 times 4, so a 120. Right? So it looks like this would give you a 1 out of 11 when all is said and done. Right? If you divide the top and bottom by 10, and then you divide them by 12, you get 1 over 11. All right, so that would be your probability there. Okay, now the next type of probabilities that we're going to discuss are if we're interested in an either-or probability. Now, first, we're going to discuss this for non-overlapping events. Okay, so we say that two events are non-overlapping, where a lot of times this is usually said to be mutually exclusive, and this means that they cannot occur together, right? So we say that, and again, let's maybe say that an example of this, right? So two non-overlapping events would be maybe something like I am male and let's see. No, I guess this isn't a good example. Let's say something like, well, let's make it easy. I am wearing a blue shirt. Let's put it this way, solid blue shirt. Or I am wearing a solid red shirt. Right? It's possible that I'm not wearing either one of these colors, but the bottom line is that if I'm wearing a solid blue shirt, I'm not wearing a solid red shirt and vice versa, right? So there's no way that those events can overlap. Now, if you want the probability of either of two non-overlapping events to occur, then the probability that one or the other occurs is just the sum of those probabilities. And again, this is another thing where you can extend this to any number of non-overlapping events. Okay, so suppose you roll a single die. We want to know what is the probability of rolling either a 2 or 3. Well, you can't roll a 2 or 3 at the same time, so these are non-overlapping. So we can apply what we just discussed here. So this would be the probability of getting a 2 plus the probability of getting a 3. And of course, each of these are 1/6. So we get a 2 out of 6, which is also 1/3. So that would be the probability of rolling either a 2 or a 3. Now, if your events do overlap, that means that they can occur together. So now what you have to do is, in order to avoid double counting, is you now have to also subtract off this extra piece here, right? So for example, the probability of drawing a queen or a club from a deck of hearts, well, you can also have a queen and a club, right? So we know that the number, so let's say the probability of getting a queen are 4 out of 52 because there's 4 queens in a deck. Now the probability of a club would be 13 because the probability of getting any suit would be 13 out of 52. But you could also get the queen of clubs, and there's a 1 out of 52 chance of that, right? Because if you were to just add these two, within the probability of the queen, you also have the club, and within the probability of the club, you also have the queen. So when you add those two, you're double counting. So that's why we need to subtract this piece off. So in this case, the probability of a queen or a club would be 4 out of 52 plus 13 out of 52 minus 1 out of 52, which would give us a 16 out of 52. Right, so that's the idea behind the either or probability when you have overlapping events. Okay, now in this next example, we have that the following 8 people are in a room. We have 2 Democratic men, 2 Republican men, 2 Democratic women, and 2 Republican women. Now, if we select one person at random from this room, what is the probability that you will select either a woman or a Democrat? So now, of course, here, we can have a woman Democrat. So these are overlapping events. So then that means in order to find the probability of a woman or Democrat, I need to find the probability of finding a woman, probability of finding a Democrat, and then minus the probability that they both happen. Well, the probability of selecting a woman, it looks like we have 4 total, so we're going to have 4 out of 8. Then the probability of getting a Democrat would also be 4 out of 8. But the probability that you select a woman and a Democrat would be this group right here, so that we would subtract 2 out of 8. So it looks like we would get a 6 out of 8, or 3 out of 4. Right, and that's the idea behind finding that probability of 2 overlapping events. Now, the last type of probability that we'll discuss in this section is when we want to find the at least once rule, right? And this will work for independent events. Now, suppose that the probability of an event occurring in one trial is P of A. Now, if all trials are independent, then the probability that the event occurs at least one time in N trials is 1 minus the probability that no events happen in N trials, right? So we're sort of using the not probability to our advantage here. And again, we can take this even further, that no A in N trials will even reduce to no A in one trial and then just to the nth power. So let's take a look at an example. So we're going to use the at least once rule to find the probability of at least one head when you toss 3 coins. All right. So one option, and I'm going to show sort of the bad option. One option that you could do here is if you want at least one head, well, you can find the probability of one head, add it to the probability of 2 heads, and then add that to the probability of 3 heads. Right? The better option is the opposite, right? Because there's only one more outcome, and that's no heads, right? So we want the probability of no heads. Oops. All right, come back. Okay, please wait. All right, here we go. So let's get back to where we were. Okay, sorry about that. Okay, so then we have the probability of 3 heads here. Now we said that the better option, since there's only one more outcome, and that's the probability of getting 0 heads, is to take 1 minus that, right? Well, we know that the probability of getting 0 heads, if we toss 3 coins, is to get all tails, which only happens 1 out of 8 times. So the probability of getting at least 1 head right, would be to do 1 minus 1 over 8, right, which would be 7 out of 8. Now, an even better option, so the best option that we could do is 1 minus probability of tails to the third, right, because we're tossing 3 coins. So what we would do is 1 minus probability of getting a tail anytime is 1/2, raise that to the third, so we would get 1 minus 1 over 8, which would also give you the 7/8 that way as well. All right. So when it comes to calculating these at least once probabilities, use one of these 2 options. Okay. In example 9, which we're getting close to the end here, but not got one more after this, I think. We want to find the probability that a region will experience at least one 100-year flood, which again is a flood that has a 0.01 chance of occurring in any given year during the next 100 years. All right. And of course, we'll assume that flood events are independent from year to year. Well, we want the probability of at least one 100-year flood. And again, so if we want to use the at least once rule, we want to do 1 minus probability of no flood in 100 years, which we could also say is 1 minus the probability of no flood in a year, to the 100 power for 100 years. So this calculation would give us 1 minus, this probability is 0.01, and I want to raise that to the 100th power, right? So if we do that, I'm going to have 1 minus 0.01 to the 100th, and my calculator is actually just rounding this right to 1, right? Because 0.01 is so small, so we're being given pretty close to 1, so pretty close to a guarantee that this will happen. And of course that makes sense, because you would expect at least one 100-year flood to occur within the next 100 years, right? Just by the very nature of it. Okay, now for the last example that we'll do for this video, we have that you purchase 10 lottery tickets for which the probability of winning some type of prize on a single ticket is 1 out of 10, right? So probability of a prize on one ticket is 1 out of 10. Now we want to know what is the probability that we will have at least one winning ticket among our 10 tickets. So of course this is probability at least one winner, right? So that's 1 minus the probability of no winner in 10 tickets. And of course we can do the same, 1 minus probability no winner for a ticket, and then raise that to the 10th power. So in this case, our calculation is 1 minus, now the probability that we don't win is 9 out of 10, right? Because the probability that we do win is 1 out of 10. So then of course I need to do 1 minus 9 over 10 to the 10th power. And if we do that, let's see, so 9 out of 10, and raise that to the 10th power. Let's see, 1 minus that, I forgot my 1. And this will give me a 0.6513. So we have about a 65% chance that at least one of these tickets will be a winner. All right, so that's the idea. Okay, so that concludes this video on combining probabilities. I hope you enjoyed, and I will see you next time.